All right, so I apologize for that. I forgot to send out the invitations last night. I just thought of it this morning. So usually I try to send them out at least a day in advance, but under the circumstances, I kind of let it get past me because I was up to my eyeballs correcting exams from the semester that just ended. And in fact, as far as I know, the semester is still going on, but here we are again, ready for another class already. So we're expecting 15 people. I see that we have 8 so far, so we'll maybe wait a couple of minutes. So anyway, in the meantime, here we are in school again, and we're going to be doing, of course, statistics this semester. It's obviously a very intense course, but it's the kind of course where you can learn it with a lot of practice. It's not meant to be too terribly theoretical. It's meant to be very practical and down to earth, but and also very luckily for us, it's also easy to apply it to real world applications. So some branches of math can be very abstract and it's hard to understand sometimes what they're for, but not so much here. This is a discipline where everything we do is designed to be useful in different areas, especially areas like business, where we use statistics all the time on a regular basis. So if you've ever had a course in economics or finance or whatever, you may have already seen this for yourselves. that is extremely important for any type of business application, but you see it also in the different sciences. You see it used heavily in biology and psychology and sociology. So this is a very important area of study, and it's going to be very helpful to you in a lot of different areas. Now, many of you are not actually purchase students, so your majors could be, something that we don't offer here. I don't have that information. I do have your email addresses and your contact information, and in some cases it does mention whether you're a purchase student or not. But because purchase, one thing, they do have economics here, but not a business school. So if you're at another school, you might actually be in a business program. And I can tell you from experience that statistics is probably one of the most important courses you'll ever take. Anyway, so why don't we do this? Let's get the syllabus out. Now, first of all, especially if you're not a purchase student, you've been given access to an account on a system called Moodle. It's many schools use Blackboard. I don't know how many schools use Moodle, but this is what we use. And so you'll find it on the website, the Purchase College website. Come down here to the academics, and here's your link, Moodle. And it is, just basically designed to keep track of all of our information. So let's go there right now, and you'll see that we have statistics, and here's all of the information that you'll need for the course. Right now, on top, you'll see there are course announcements, reminding you of the information that we need for this class. And here, for example, it mentions that we will start at 10 o'clock each day, and we'll meet from 10 to 12:30. Now, by the way, 12, that's a long class. We're going to have a break in the middle somewhere. Don't worry about that. So it's not 2.5 hours straight through. There's a little break in the middle, but by doing it this way, we have plenty of time to get the work done. We also have time to get the assignments done, in spite of the fact that we're basically in a holiday season where you have other things going on as well. So, the amount of assignments you'll have won't be, in my opinion, it won't be too overwhelming. You should have plenty of time to get everything done. And then you'll also have the ability to learn the material just as if you were in a normal full semester course. So whenever there's an announcement, I'll post it here. I don't know if this automatically sends you an email or not. That I'm not so sure about. So what you should do is periodically check for announcements, just in case there's something. Now, by the way, if there's something critically important that you need to know about right away, I'll also send you an email directly, not just put up an announcement. That way I can ensure myself that you are getting the information when you need it. Now, having said that, you know how email can be, especially if there's attachments involved. Often emails can wind up in your junk box. So you want to be careful, take a look and see if it's in your inbox or possibly in your junk box. So if I do send you something with an attachment, there's always a risk it could get kicked into the junk box. It happens all the time to me. So those are your announcements. And then the actual materials are right here where you can just simply, download them. And you'll see that we will be using PowerPoint very extensively in this class. All of the notes, I have written them for PowerPoint, and they're based on our book, which is described in the syllabus. You don't have to feel like you must buy the book if you don't want to, because what we need is here in these slides that I put together for you. And everything you need will be in here. So in other words, the tests will not ask any questions. They're not based on these slides. So you have a complete list of everything you need in the slides. So you can feel free to download them. You can do whatever you want with them, print them out, whatever. They're yours to keep. And then for each chapter, there'll be a problem set, which you will be asked to complete and turn in by email, of course. Now, this is where we have to be careful. One of the unfortunate things about being online is that you have to find a way to submit your assignments and your exams. Now, email works to a degree, although it can be a little erratic. You're going to be writing out answers probably by hand. Most likely with these types of problems, you'll be using a pen or a pencil on paper. So what you can do is you can either take pictures of your work with a phone camera, and they usually work pretty well. as long as your handwriting is clear. But there also exists software products that you can buy. Let me mention one of them here, one or two. Now, I didn't find these myself. Students in my past classes have recommended these to me, and these are basically scanning apps. And let me search my phone right now, because I know from experience they work pretty well. You're basically turning your phone into a scanner when you use these. And let me just quickly find one of them for you. You've got, oh my God, there's more than one. There's a PDF, there's something called where should I write this? Hold on 1 second. I was just going to list some of the ones I have on my phone. I don't know how well they work, but I do know that in the past, people have used some of these and they told me that they worked well. There's one here I see called My Scanner. And again, these are apps you can buy for your phone. And what they enable you to do is turn these into not just pictures, but scans as if you had a physical scanner. And which it seems to work very well for documents. All right, hold on 1 second. Now I've lost my place. There's more than one. I know there's more. You may know of some yourself. I have one here called My Scanner, Doc Scan, Adobe Scan, Code Scanner. Well, you get the idea. There's more too that I can't find right at the moment. But if you want to use a scanner on your phone, and I believe these are all free, you're basically taking your phone and you're swiping it over the document like you would with a physical scanner. And all of a sudden, before you know it, there is a document which has a very high level of quality, which you can then send to me directly. Now, having said all that, if you own a printer, chances are it actually has its own scanner anyway, which you could use as well. You can turn that into a PDF file, and then you can scan it to me directly by email. So there's a lot of options. Okay, so all I ask you to do is just make sure your handwriting is clear, and then look at the document before you email it, because sometimes what people don't realize is that there might be glare on it and it makes it hard to read. So before you send anything to me, make sure you can read it yourself. Okay, so with that all being said, we shouldn't have any real difficulty in that area, but it might be something that takes a little getting used to. So what else do we need to know? Let's go back to Moodle for a second. And as you can see, like everyone else, I have way too much stuff open, so I can't find anything. There we go. All right, so now you notice here I have our syllabus. I have the first chapter that we'll be covering, which is chapter 3, and chapter 5 is next. There's the first problem set is here. You can feel free to start working on it as soon as you want to. I'll try to have these due, let's say, every week. Like I said, I don't want to rush you too much, especially when Christmas is coming right around the corner. But, you want to get started on these sooner rather than later. And so this is the first one. This is the chapter 3 problem set. And let's see, what else do you need to know? Well, let's take a look at the syllabus for a bit. Here we go. Now it's the usual stuff. It's all the introductory material, information about how to get in touch with me, my email address. It tells us there's an online class. When do we meet? This is the book that our notes are based on. Here we go. Calculators. Here's an important topic. You probably already own a decent calculator. If you don't, you might want to look into this Texas Instruments TI-83 or 84 series, because they're really well set up for statistics. They're not the only ones in the market, but I strongly recommend, if you don't already have a proper calculator, this is the one you should get, because it's not only useful for statistics, it's also useful for business applications as well. And of course, it does everything you can imagine with scientific applications, if that's what you're interested in. But that's one of the better choices. And as we go along, I will go over that with you, how to use this calculator to get our results as we need them. Okay, so anyway, so what are we doing in this class? We're going to cover about, let's see, 1, 2, 3, 4, 5, 6, 7 chapters. This is the traditional set of chapters you would cover in any introductory statistics course. It's not meant for any specific application. It's just an all-purpose statistics class, which you can take back to your school or your major and use it in other areas and get credits wherever you're going to school. And it's a great way to knock off 3 or 4 credits off of your schedule and get this very important topic covered during the Christmas break. So the grading is very simple. We'll have a group of problem sets or chapter problem sets, which you'll do for about 35% of the grade. There'll be a midterm and a final, which you'll do at home and then send it back to me. And so every day we'll have the same routine. We'll have our online class, and then we will go over the material, and then I'll give you the assignment. And at some point we'll have our first exam. Now, this is where online really is very helpful though. Everything we're doing here is being recorded. So let's say that for some reason you can't show up on, at 10 o'clock, or there's something going on and stops you from getting here. Or maybe you have to work, who knows? There could be a lot of reasons. Not a problem. All you have to do is go to my YouTube page and you'll find this recording. And the reason why it's on YouTube and not Moodle is because apparently I've been told that Moodle does not have the capability of storing massive files, which these recordings certainly are. So here's my YouTube page. And it's all you need to know. Now there's apparently all you need to know is my name to get into my YouTube account. All right, if you go to YouTube and look for my name, it'll take you to not these music videos here, but now what I'm doing here is I'm setting up what's called a playlist. The reason for that is because I have so many videos on here. You'd never find it if I didn't do this. Like, you can't even imagine how many videos I've accumulated over the last 2 years because of the COVID. So rather than having you search through all these videos, there's a lot of them you can see. What I'm going to have you do is go to a playlist, which I will be setting up for this class. And within that playlist, you can see now I haven't set it up yet. You need to have the first video ready to do this, but it'll look just like this one. Oh, sorry, that's not what I wanted. The playlist, just here it is, view full playlist. It's literally a list and only contains the videos for this class. Okay, so you can grab it and watch it at your leisure. And even if you were in class and you just want to go over something again, well, here it is. So this is the great thing about online. This is something you don't get in the classroom unless you've got all the equipment there. The recording can be hugely helpful. And so this way you can repeat or watch it again or do whatever you need to do. Now, having said all that, if you just want to add a quick question, you can send me an email. Here it is. My email is right here. By the way, I just want to mention one thing here. I did not send you your invitation from my purchase account. I'll tell you why. Because with a roster like this, I've got a huge list of names, and regular Gmail will allow me to paste them all directly into the address line, whereas the purchase account will not. I'd have to type them individually to send them to you in my purchase account, and that could take a long time. So I just send it to you directly from my own Gmail account. All right. So just be aware that you can reach me either on my official purchase account here or my Gmail account, which let me write this down for you on the screen somewhere. And it is still not big enough. All right, that's my personal Gmail account, which I'm using to send out the invitations, as I mentioned, because of for whatever reason, the purchase email isn't set up this way. You can't just set up a group of names and let it all go at once. They have to be entered individually. And so that's just not worth the trouble for me. So you can write to me on either one of these email addresses, but you'll be receiving your invitations from my personal account. And if you're really stuck, I mean, if you're really struggling and you just need more help we can arrange a separate online session anytime, as long as we're both available. I can set up one of these meetings just for one person or a group of people, and then we can go over the material again. So it would be the equivalent of office hours. Okay, so, I mean, this is very complex material, and, you might need to go over it more than once. So don't hesitate to reach out and say, listen, can we go over this chapter again? And, it's just a question of picking a time that's mutually convenient. All right, so I'm guessing that by now, with everything that's been going on the last 2 years, this is probably not your first online class, but if it is, and there's something you're not sure about, again, you can just reach out and ask me, because, there's a lot of things that you might not be aware of. It's like the technology isn't always as user-friendly as they think it is. You often find yourself needing to find just the right little picture or the right button, and God forbid they should have labels on any of this stuff that tell you what they mean. So just let me know if you have any issues or any difficulties. Anyway, so I think that's enough of that. We've looked at our syllabus. You can read through the rest. It's just a brief description of what's going on in each chapter. We don't need to do that now. There's more difficulty, everything. Anyway, so I think we're good here. So why don't we do this? Like I said, we're going to start with chapter 3 today. Now, the material today is meant to be the introduction to our course. There's a couple of earlier chapters, but it's, a lot of, fluff, really. Things you could read on your own if you wanted to, but this is where the material starts. Now, in this chapter, we're going to introduce a lot of new terminology and notation that we'll use throughout the course. So it might not be the most exciting chapter in the book, but it is one of the more important ones. And also, you'll give you a chance to get used to what statistics is like. And so some of this you may have seen before in another class. It is possible that you bumped into this in high school, because some high schools do offer statistics. But if that's the case, well, there's nothing wrong with a little review. But if it's brand new, we're going to go through it slowly and carefully. So just be aware, of course, you'll have all the slides available to you, and you'll be able to watch the videos at your, whenever it's convenient for you. And I'll always be available for, like I said, email questions and possibly online Zoom sessions. So you should be all set. And so when 4 weeks are over, you'll have all this great background, and you'll have 3 or 4 credits, depending on your school, that you can apply to your GPA and reduce the difficulty of your schedule in the spring. And so I congratulate you all for being willing to work hard during the Christmas break and get something useful done. This is really important. So anyway, let's begin at the beginning. Let's introduce chapter 3. And so you can see what we're doing here is what's called statistical description of data. Now, data can mean any type of information. In these examples, I typically focus on more business applications, but this could be applied, like I said, to so many different areas of study. And so we're going to start out by introducing 2 of the most important concepts in statistics. We're going to show that there's 2 types of data that we might be interested in. We may be looking at a population or a sample of data. As it turns out, a population is actually more general than the word population that we tend to use, which means a group of people. In statistics, the word population means a collection of measurements or other outcomes that we are interested in studying. For example, what if the US government is trying to do a study to determine if the average age of all Americans has increased in the last 20 years? In other words, is the population aging? Are people living longer because of medical breakthroughs? How do we find out? Well, the data that we are interested in studying would be the ages of every American. And of course, that is a gigantic population. Well over 300 million people live here. So the population would be not the people themselves, but their ages. Now, the problem with this is that that's a lot of information. Is it really necessary? If the government just wants to get an idea of whether or not the population is aging, It's probably not necessary to count every single person in the country. Most likely what will happen is that they will take what's called a sample of data, which means they will randomly pick, let's say, 1 million people scattered throughout the country and examine their ages. And the idea here is that if the people that they chose were chosen in such a way that they really represent the overall population, their ages should be a good representation of the entire population. So that group of 1 million people would be called a sample, right? It's not the entire population, but if it's chosen carefully, could do a very good job of showing us what's happening in the overall population. So we'll often see in statistics that most of the information that we have to work with is coming from samples rather than populations. It's very unusual that we actually take the trouble to collect every element in a population because it's typically so large and typically it's not even necessary. So most of the time we'll focus our attention on samples. Now you can see that we're defining it with a fairly technical term here, a subset. Now, right then and there, I just want to mention that statistics, to a certain degree, is based on an area of math called set theory, which you are all familiar with. But just to stir up your memories, I have written here a very brief overview of some of the more important properties of sets. Okay, so let's just quickly review this. This is meant to be a little side detour into the world of sets, which may or may not be familiar to you, but I suspect that you've all been at least introduced to these concepts at some point along the way. All right, now we're going to look at these sets. Now, you might remember a set is defined as simply a collection of objects. Typically, they're numbers. And you'll notice how they're written. A, for example, is the set that contains the 5 numbers 1 through 5. It's written with these symbols, which you might recall. I'll sneak this in over here. This symbol is called a brace, believe it or not. If you didn't know that, those are referred to as braces in math. They contain a collection, a set. And set A is the elements 1, 2, 3, 4, and 5. B is the set 1, 2, and 3, and C is 5, 6, and 7. Now, the logic here is that B is a subset of A because all the elements in B are also elements of A. On the other hand, C is not a subset of A because even though they both have a 5 in common, the set C is not completely contained within A. So that's how you can tell the difference between two sets that are subsets and those that are not. So in a similar way, you can think of this class as a subset of all the students who are currently taking classes at SUNY Purchase. It's just a part of the total. Anyway, so we'll review more of the set theory later on, but right now, for our purposes, this is all we needed to remember. Okay. Now, here's another one. What if a school wants to study the GPAs? Now, it doesn't seem possible, but schools are worried about GPAs. They are always afraid that the GPAs are getting too high. Now, why would that be a problem? Well, to them, it's a sign that the teachers are grading too leniently. And that means, well, let's just say that every school wants to be perceived as being academically rigorous. And it always concerns the school if GPAs are creeping up because it might mean that the teachers are being too lenient on the students. So they periodically study GPAs. And if they find that the GPAs are rising, they want to know why. Now, it might just be that the students are simply better. They're accepting better and better students. But if they find out that the teachers are letting the standards slip, well, that's not a good thing. In fact, some schools actually brag about how low their GPAs are because they want you to think that it's tough to do well in this school. So let's say this particular school decides, you know what, we don't have time to look at every one of these GPAs. Why don't we randomly pick 10 students and let their GPAs tell us roughly what's going on for the entire school? Now, in this case, most likely that sample size is probably a little too small unless this is a tiny little private school, with only a few hundred students going there. Normally, the sample size would be bigger than that because 10 is a very small collection of people. The problem with having such a small sample is that you might accidentally pick the 10 students with the highest GPAs or the lowest, and your numbers are not going to be very meaningful. But that does qualify as a sample. Those 10 students are a sample that represents the entire population of students at that school. So these samples are being used to estimate the properties of the underlying population. The accuracy of this process depends on how closely the samples reflect the population. So that's a key detail. Now, by the way, here's an example. You may not have noticed this, but whenever there's an election coming up, especially a presidential election, you're seeing polls all over the place. There's constant discussion on TV about polls, like, X% approve of this candidate and X% approve of that candidate. Polls like that are based on samples. In other words, if they tell you that, for example, 32% of the population likes candidate X, they didn't call every single voter and ask them about that candidate. What they probably did was they chose a sample, and you're seeing the proportion in that sample who voted for this candidate. In fact, how do you know that? Let me just show you quickly. You might see something like this on your TV screen. It might say something like the approval rating for, oh, hold on one second. I just realized I forgot to do something. I have this wonderful device. It's a tablet that lets me write on the screen, but I just realized it's not plugged in. Hold on one second. In order to plug it in, I have to eject something else. Okay. All right, 1 second and I'll be ready. There we go. All right, so this is what I was going to say. You see on the screen, it's splashed all over the place. Here's candidate X with his picture or her picture. And it says 32% approve. And then down in the bottom, with the tiniest possible print, it might say something like this. Plus or minus 3%. What that means then is that what they're really saying is that while the estimate is 32%, since this is only a sample, they're telling us that there's a very real chance that this could actually be somewhere between 29% and 35%. In other words, this is 32% minus 3, and this is 32% plus 3. The 3% is called sometimes a margin of error. And this reflects the fact that this is only a sample, not the full population. So they're trying to give you a sense of how much uncertainty there really is associated with this estimate. I'm saying we think it's 32, but we're willing to say that it's bound to be, it's highly likely to be between 29 and 35%. Just to give you a sense of how much error there's likely to be in that estimate. If they chose the sample very well, this margin of error could be quite small. If they weren't terribly careful, this margin of error could be quite large, and then the number doesn't really mean a whole lot. So they really have to be careful. And in recent years, political polling has lost a lot of its, let's say people are starting not to take it quite as seriously because there's been some catastrophic mistakes being made. Whereas other types of samples tend to be a little bit more accurate, like marketing research leans on this all the time. They might try to find out like how many people prefer Coke to Pepsi, let's say, or how many people prefer vanilla to chocolate. That type of research tends to do very well because people realistically might say they like a candidate. Maybe they don't really mean it, maybe they change their mind, but when people are asked about flavors and colors and things like that, they tend to be very accurate. So, this whole area of sampling is actually a very major part of statistics. And in fact, it's almost like a separate area because it's so important and there's many different ways it could be done. We don't have time for that in this class, but we need to understand what sampling is, what samples are and how they work and why they're so important. But anyway, now it mentions here properties. What kind of properties do we want to know about a population? What exactly are we talking about? Well, like for example, when the US government was looking at all the ages, what they were really interested in was the average age, okay? They didn't really need to know the range of ages, for example, from the youngest to the oldest. They were only really interested in the average. So that could be considered a property of our population, the average age. So we're going to see several different measures that are designed to help us understand the properties of a sample or a population. So the first group of measures that we're going to look at are known as, collectively, as measures of central tendency. So these will be the first measures that we will be introduced to. And what they're designed to do is help us understand the values in the center, what values come in the center of our data or the middle, okay? In other words, the average is an example of this because what are we looking for? We're looking for the age that's in the middle of our sampler data. So these are measures of central tendency. They're called that because they're trying to help us figure out where is the middle or center of our data. And there's a lot of useful information you can get out of that, but for many applications, what we're really after is one of these key measures of central tendency. Now, when I show you the list, I'm going to guess that you've probably seen these terms before, okay? Maybe not, but most likely you've seen them before. And so now what we're going to do is formally define them all so you understand what they represent and why they can be useful. All right, here we go. Mean, median, and mode. And by the way, I just want to mention that the word mean is simply another word for average. In statistics, we have a lot of concepts that have more than one name. It happens a lot. This is one of those cases. The center of the data, the mean, is just a fancy word for average. And I'm sure that everyone has an intuitive idea of what an average is. Well, we also see these other two ideas, the median and the mode. Now, these other measures are not used as often as the mean, but under certain conditions, they can prove to be very, very useful. That will depend on what kind of data we're looking at. Okay, so these are the three that we want to consider. Now, before we go any further, I just want to mention that in each case, we want to understand how to calculate these measures for both samples and for populations. Even though we won't be working with populations very often, we still need to understand how to calculate these measures for them. All right, now, that being the case, we're going to start with the sample mean. All right, so just to let you know what's coming, we're going to start by looking at the mean of a sample, and then we'll follow that up by looking at the mean of a population. In order to do this, we're going to introduce a formula. We're going to reduce this to an actual formula, which has some interesting components to it. All right, so we're going to see a new formula, our first formula of the course, which is the sample mean, and you might recognize some of it, and some of it might be new to you. Okay, so let's take a look. Oh my God, look at this thing. What is this all about? What's going on here? Well, first let's note that this X with a little bar on top of it is actually called X bar. And in statistics, a bar means we're taking an average, okay? This is the symbol that we typically see that is meant to represent an average or a mean, okay? That's the starting point. Now, xi. So what is that all about? The elements of a sample are assigned what's called an index. So let's just say that, for example, we have 3 students and 3 GPAs. Student 1 has a GPA of 3.2, student 2 is at 3.4, and student 3 is at 2.9. That's our sample. So this first GPA would be, these are considered to be the letter I, or index. This GPA is X1, X2, and X3. The X means that it's a GPA. The subscript or index tells me which student I'm referring to, okay? So the reason why we're doing this is because if we try to use letters like A, B, C's, W, Z, whatever, we would run out of letters very, very quickly. So instead, the way we do this, let me just make this a little neater, is we use X to represent the variable of interest, which in our case is the GPA, and then that subscript or index tells me which element I'm looking at. Okay, so let's say student number 1 is John, student number 2 is Bill, and number 3 is Mary. So rather than using the name, like imagine trying to write an equation, John equals 3.20. No, John's GPA is X1, Bill's GPA is X2, and Mary's GPA is X3. Okay, so in this formula, that's what this xi means. And it means this represents a single element in my sample. Now, the big mysterious symbol right here, this is actually the Greek letter sigma. And it is often referred to as the summation operator because it tells us to add something up. And it also contains this information, I equals 1 to n. That means the index that we'll use is I, which will start at 1, go to 2, 3, 4, all the way up to n, where n is the number of elements in the sample. So if we have 10 elements in our sample, then I ranges from 1 to 10. So in other words, everybody gets a number. That's what I'm saying. In this case over here, n is 3 because there's only 3 students in our sample. So all of this put together is simply telling me that in the numerator, I'm just adding up these x's. So in my GPA case, I'd literally just add up 3.2, 3.4, and 2.9. And then in the bottom, I'm dividing by 3 because I have 3 elements in my sample. So that means I'm running out of space here, of course. Let me try this. In this case, I would have 3.2 plus 3.4 plus 2.9 over 3. And that, well, let me get out my calculator real fast. By the way, you all have a really nice calculator built into your iPhone if you didn't know it. Let me show it to you in a second. Let me just, when I'm through calculating this average, 3.2 plus 3.4 plus 2.9, that's about 3.17. So that means in this sample, the average GPA is approximately 3.17. How did I do that? Well, the formula looks very scary, but all it's doing is saying, listen, just add up all your elements and divide by 3 because there's 3 of them. It's that simple. So while it's a scary looking formula, it's actually conceptually very easy. Well, that's what we like to hear. It's easy. All right, now let me show you, in case you don't have a fancier calculator in front of you, let us take a look at our phones real fast. See, even I've got one. Oh, there you go. You see that button, calculator? Now, when you hit this button, you're going to get this very basic calculator, which is fine, but to get to the one you really need, whoa, look at this. You turn it on your side and all of a sudden you have at your fingertips a very powerful scientific calculator. Wow. And you know what? You don't actually, if you don't own the Texas Instruments calculators, you don't have to buy one. This one doesn't have quite the capabilities of the Texas Instruments, but it's pretty good. So if you don't want to buy a calculator, I would use this one. Okay, just don't forget to turn it on its side. That's where all the power is. All right. So who knew that? How many of you knew that? I don't know. But now you do. The secret is out. Here you go. That's all the power you'll need. All right. So here's, oh, by the way, let me just, we're going to quickly go over now the summation operator. Here's a sample of 5 elements. We don't know what they represent. It doesn't really matter. We've got 5 elements listed as X1 through 5, and we're going to calculate the sample mean. We're assuming this is a sample. By the way, it's often not obvious if our data is a sample or a population. You really have to be told which one it is. It's not the kind of thing that you can really reasonably figure out on your own in many cases. So any problem you run into, it'll have to tell you whether this is a sample or a population. Here we are, 5 elements. And so the summation operator applied to these would simply say, well, guess what? Add them up. Okay, so again, what it's doing is really saying, however many elements you have, n, go through them all, 1, 2, 3, up to n, and add them up. So here, this is element x1, x2, x3, x4, and then x5. And you can see they add up to 10. So how do I calculate my sample mean? I'm almost done. I just take my sum. Remember, the formula was take the sum and divide by the sample size, which in this case is 5. And that just simply means there are 5 elements. So I'm going to divide that by 5, and that's going to give me 2. And it's that simple. So in spite of its fearsome appearance, this is a very powerful tool for summarizing or representing equations that can do a lot of very important things. All right, now for some of the more advanced measures, though, we will need to do much more complicated things with our summation operator. So let me show you some of the other ways we can use this operator. All right, and take my word for it, you'll need this later on in the chapter. What if I don't want to sum up the elements themselves, but I want to sum up their squared values? And you can see here, that's what I'm doing. Each element is squared before I add them up. So what we do is we write this as the summation of xi squared, or x1 squared, x2, x3, all the way up to xn squared. I now plug in the actual value of x1, 2, 3, 4, and 5. Square those values and add them up, and I end up with 40 instead of 10. The key is right here. That's the clue that we're adding up not the x's, but their squared x's. And by the way, you can do all kinds of things with this operator. It's really much more flexible than you might think. All right, then. Now, here's a twist. What if I want to do the opposite? What if I want to do the following? What if I want to add up the individual elements and only at the end square them? So you see the difference here is that instead of having this, let me just quickly copy this so you can remember. It's a subtle difference, but with the one on top, we're squaring the terms before we add them. So let me write that in here in English: square, then add. What are we doing here? We're adding all the elements, then we square them only at the end. Now that is different, isn't it? And you can tell because this interior part tells me to add up the x's and only then square the final result. And you can see instead of getting 40, I'm getting 100, because when we added these up, I get 10 squared, which is 100. So we have to be very, very careful with this notation. All right, so far so good? All right. Now there's another version of this I want you to see, because this is directly related to the measures that are coming up later in the chapter, by which I mean what? All right, well, let me give you a minute to catch up. All right, now this one's a little messier because we're really doing two things before we add them up, instead of just one. So watch what happens here. Suppose that I want to take each x. Now, by the way, k is a constant of some kind. We'll have an example in a minute, but subtract k from each element. Square the result. The results, I should say, and then add them up at the end. All right, so in other words, whatever the x minus k is, for each x, subtract k, then you square the difference, and only then do you add them up. Which sounds like a nightmare, but when I show you this next example, you'll say, oh, that isn't that bad. Okay? You just have to be methodical, let's say. All right, so I'm going to show you the data we were using a minute ago, the sample, the 5 elements, but this time we're going to subtract a specific constant. All right, let's try this. Let's go back to the original data. Remember, we had x1 is 2, x2 is -1, x3 is 3, x4 is 5, and x5 is 1. Now I'm going to go through each one of these. This is x1, x2, x3, x4, and x5. And then in each case, I'm subtracting 3. Right? And within the parentheses, I'm subtracting. Then I'm going to square that difference. So you can see now what I've done here in this next row is I put in the differences, and then I will square them. Okay, so here I'm squaring these differences. and then add them up at the end. And you end up with 25. Now, that's the scariest one that we're going to see, by the way, in this chapter. It could get a lot worse, but we're not going to do that. We just want the ones that we'll need for this chapter. Okay, so we will need this. Otherwise, we wouldn't bother to do it. All right, so that was our little tutorial on the summation operator. But remember, you're going to see this formula. It'll show up in a lot of formulas in statistics. So that's why it's so important to be comfortable with it right now. All right, so just getting back to the example we had before, we finally bring all this together. We calculate the sample mean for this data that we've been using. And as we saw before, it's equal to 2. Because we simply add up those elements and divide by the sample size, which is 5. Okay, so n can be called the number of elements in the sample, or we often refer to it as the sample size. Okay, good. And of course, you have to have the n up here too. Whatever's going on down here is what we're going to see up here. There's going to be the same number of elements in the sum as in the denominator there. And if you notice, we always start at 1. If we don't, we'd be leaving something out. Now, I mentioned before that for every one of these concepts, we need to understand how to apply this to a sample and to a population. Here, the formula for the population mean is coming up next. And when you look at it, you'll realize the steps are the same. What's different is some of the notation in the formula. So let me show you what I'm talking about. So first thing you'll look at and say, wait a minute, what happened? Well, the X bar is gone. This is the Greek letter mu, which is the equivalent of M in the Roman R alphabet, that is, which is the Roman alphabet. And another thing that's different is that the lowercase n's have been replaced with uppercase n's. So from now on, just remember that lowercase n means the sample size, and capital N is the population size. Now, you might wonder, why are we doing this? Why don't we just call them both lowercase n, for example? Because there are formulas that we will encounter that need both of them. And so we need to have a way of telling them apart. Okay, so lower is sample size, uppercase is population size. Now, also, if you notice, the X bar was replaced by a Greek letter mu. So the convention is this: we reserve the Greek letters typically for population measures. The Roman alphabet, which is more or less what we're using, with maybe some minor modifications, we're using the Roman alphabet. And this is going to be used for sample measures. Yeah, we kept their alphabet. We did not keep their numbers, though. As you recall, remember Roman numerals? Yeah, we don't use those anymore. But we did keep their alphabet. You might recall that the Romans invaded Britain in AD 54. And from that point on, English is very much more resembled Latin than prior to that. But yes, we retained their alphabet. I don't know what alphabet they were using before the Romans got there, but it's not what we're using now. All right, so what I'm getting at here is that it's the same formula, though. If you notice in the numerator, we're simply adding up some of the population elements. And then this is the population size. So it's the same formula. It's just the notation is different. Okay. All right. Now, because it's the same formula, we don't really need a separate example because it's the same procedure. You're just adding up all the elements and dividing by the population size. So instead, what we're going to do next is introduce a new kind of mean. Now, the average or mean that we just calculated is used in many applications, but there are times when it could be streamlined or simplified a little bit. We sometimes see the use of what we will call a weighted average. Now, weighted averages are useful in many applications, in particular when there are elements in our sample or population that are, let's say, repeated many times. And another great example of this is your GPA. You may not realize it, but your GPA is a weighted average. Now, what do I mean by that? Since not every class you take has the same number of credits typically, there has to be a way of adjusting for the fact that some classes are, let's say, only worth 3 credits and some are worth 4. And so the way they calculate your average is not to add up all the scores and divide by the number of classes you've taken, but to actually multiply each grade by the number of credits you're earning, and then at the end divide by the total number of credits you've taken. So I have an example of that down here, by the way, so we'll get to that in a few minutes. Here I want to start with a slightly different example. In fact, you may have been wondering about that yourself. How are they calculating my GPA? I don't get it. Well, we're going to find out in a few minutes exactly how it's done. But what it does is it involves adjusting for the number of credits that each course is worth. Now, let's look at the formula for sample weighted average. Now, you notice there's something new in here. WI is the weight. I'll put that in quotes before we haven't defined it yet. Each element has a weight associated with it. This weight reflects its frequency in the sample, or let's just say the data, because it works for populations as well. All right, let me just fix this a little. So in other words, some of the elements might show up more often than others, and this is a quick and easy way to take that into account. So other than that, none of this is new. This is still X bar because it's a sample mean. In the numerator, we have the sum of the weights times the X's. In the denominator, we clearly have the sums of the weights. And when we divide that out, we'll end up with our weighted average for a sample. Now, there's a separate formula for a population, which again only involves changing the notation ever so slightly. All right, let's take a look at it. And you can probably anticipate already where the changes will be. The lowercase n's will become uppercase because that now refers to a population, and X bar will again be replaced by the Greek letter mu, which represents a population mean. Okay, so yes, again, remember, this is our population size. And this is our population mean. It's a weighted average or weighted mean, but it still represents a population. All right, now here's an interesting example. We're going to do this one first, and then we'll get to our GPA example. This is a lottery. Okay, now the way lotteries are typically structured is that there's often a grand prize, but there's usually more than one prize. I mean, like this is how they get you to come in and buy the tickets. One gigantic prize, and everyone's like, wow, I'm going to win this $100 million prize and be rich. But they often have other prizes as well. They have a series of smaller prizes, which you can still win. So it's not like you're either going to get the grand prize or nothing. There's typically other prizes available. But let's say here we have a small lottery. This is not the New York State Lottery. This is some other lottery where there's a single grand prize of $1,000. There's 10 prizes of $500 each, and there's 100 prizes of $10. What is the average prize received by a lottery winner? Now, one thing I do not want to do is add up 1,000, 510, and then simply divide by 3. That's going to give me a very deceptive result because there's only $1,000 prize and there's a lot of $510 prizes. So I need to try something different. I must take into account the fact that there's so few large prizes and so many small prizes. So the way to do that is to create a weighted average. That's an example. Now, if there were only 3 prizes, then this would be easy. I'd add them up and divide by 3, but there's a large number of prizes with different values. So the way we're going to set this up is that the prizes themselves will be the X's. Okay. So we'll call X1 1,000, X2 is 500, X3 is 10. These are the weights. There's only a single $1,000 prize. There are 10 $500 prizes and 100 $10 prizes. So this is how we take into account the different numbers of prizes. The weights are the numbers of prizes of each value. That's how this works. So think of these weights as frequencies. At least in this case, they're frequencies. They don't have to be frequencies, but that's often when we use these weighted averages, when we need to take into account different frequencies. Well, now all we have to do is plug these numbers into our formula. Now, because these are all the prizes, we can think of these prizes as a population. Okay, it's not a sample because it represents all of the prizes. So let's use, the population formula. And if you notice, what do we have? The weight of the big prize times its value plus the weight of the $500 prize times its value plus the weight of the tiny prize. And then in the denominator, we have the 3 weights. So let me just quickly, hold on one second. In the numerator, we have 1,000 plus 10 times 50 plus 100 times 10. No, that's not right. It looks like we've got 7,000 over 111. Yeah, that's where that's coming from. So what it's saying here is the average prize is only $63.06. Now, that's obviously very small compared to the grand prize of $1,000. But the reason why it's such a small number is because there's so many more small prizes than big prizes. Now, what that tells us too is that if the ticket costs $100, then we don't want to buy this ticket, do we? No. I mean, yeah, sure, you might get the big prize, but on average, you're going to lose money then. All right. So now let's move on to the GPA example. It's a little bit different now because the weights are the number of credit hours. And every school does this differently, but most schools the courses all either have 3 or 4 credits. It depends on what they are, what department they're in. For example, math classes tend to have 4 credits. Social science classes tend to have 3 credits. Heavy science classes like chemistry and physics tend to be 4. If there's a lab involved, there might be more. But let's just say that at some mythical school, this is what we have. We have a student who took 4 classes this semester, and English and psychology were worth 3 credits, Calc 1 and physics are worth 4, and these are the student's grades. What is this person's average? Well, because the credits are different, we can't just simply add these up and divide by 4, because it would actually understate the average in this case, because if you notice, this student had the highest grades in the courses with the largest number of credits. So adding them up and dividing by 4 is not going to give us the right answer. So how would you set this up? Well, these would be our weights, and these would be our x's. Okay. There you go. So let's go find, and let's treat this semester as the entire population. So those are the weights and those are the x's. And then we plug them into the population weighted average formula. And let's see how this person did. All right, here we go. So once again, these are the weights. And these are, the second number is the actual GPA for that course. All right, and then these down here are the weights only. In other words, the student took 14 credits, and the total weighted value is 47.9. So this person has a GPA of 3.42. And again, I would remind you that if we simply added them up, let's go back real quickly. I'm going to do this right now in the calculator. If you just added up those 4 grades and divided by 4, you would have ended up with only 3.32. So that would have cheated the student out of 10 points. So this is what we mean by weighted average. You see them all over the place. But usually the motivation is that either each value doesn't have, each observation, each X isn't weighted the same for some reason, like with GPAs, or else maybe some X's occur more than others. So this is a very powerful technique. All right, now remember the list that we put together of the 3 measures of central tendency: mean, median, and mode. We're about to start the median. Now the median is a little bit trickier because it does not have a formula as such. It is simply a procedure. And we have to ask ourselves, why are we doing this? When we're done, we're going to, at some point, we're going to compare mean and median to understand what their benefits are. But like I said before, now this is a very long class. So, and it's a very complex class. So we're going to have a little break every session. I think right about now is a good point to stop for a few minutes and get some refreshments maybe. before we tackle medians. So I'll tell you what, why don't we agree to come back here around, let's say 11:30, and then we'll have one more hour to finish up for today. And I think that will be quite sufficient for the first day. So let's stop right about here, and I'll meet you up again at roughly 11:30. Okay, that should give you plenty of time to eat or drink something. I know you're at home, so you shouldn't have any trouble with that. So I'll see you all in a little bit. All right, in the meantime, I'm going to pause this recording because otherwise you'll get 15 minutes of blank space. All right, there we go. Ah, all right, we're back. So now we can dive into the median. And basically what this is a number that literally just divides the data in half. In other words, it's a number such that half the elements in the sample are greater than that median and half are below. All right, so it's more like, instead of an average, it's more like a divided line. So you can chop the data in half. You have the upper half and you have the lower half. The median separates the upper half from the lower half. Now, this one is a little bit more challenging to calculate. Well, I wouldn't say it's more, it's just different because there's one extra step that we don't have to worry about when we calculate the mean. And what that step is, we have to sort the data from the smallest value to the highest in order to do this properly. All right, so you have that extra complication here. All right, so let's go back to our data that we had earlier, the same 5 elements. And so the first step is to sort them from low to high, as we've seen before, or as I mentioned. And so the original data is now going to be -1, 1, 2, 3, and 5. Now, what are we looking for? We're looking for the value in the middle, literally in the middle. And in this case, that appears to be the 2, because the 2 divides the sample in half. Half are below and half are above. So this was a very simple case. So here I've shown it to you graphically, so you can, obviously see that the 2 is in the middle. Now, here's the complication though. This was possible because we have an odd number of values in the sample, 5. But what if there had been an even number of values? Let's say 6. What would we have done? All right, well, let's find out by looking at another case. And so here it's different. The values themselves are different, but we also have 6 elements instead of 5. All right, so here we go. These are the 6 elements. And once again, the first thing we want to do is sort them from the lowest to the highest. And by the way, of course, that's not that difficult when there's a small sample, but with larger samples, it becomes more awkward. So anyway, what do we do differently? Well, if you sort them out from low to high, you can see it's 0, 1, 2, 3, 4, and 6. Because there is no value in the center, what we have to do is average out these 2. And of course, you can see the average of 2 and 3 is 2.5. So in this case, the median is 2.5. Even though there is no 2.5 element in the sample, 2.5 does in fact divide the data in half. Okay, so you can imagine it appears right here, and half are greater, and half are smaller. And so that's really all you have to do with the median. Sort them out, and then if there's an odd number of values, just find the one in the center. If there's an even number, you average out the 2 in the center, and that's it. It's that simple. But the complication, of course, is that you have to sort them, and then you have to decide whether you have an even or an odd number of values. Now, if you notice, there's no formula for this. It's simply a set of steps that you follow. I guess nobody figured out a way to turn this into a formula, and so we just have to remember how to do it. And for that reason, we do not have a separate process for the population. So in other words, the sample median and the population median are calculated in exactly the same way. Okay, so the population median is calculated in the same way as the sample median, and there's no formula for either one of them. All right, I don't know if that's disappointing or not, but we don't have a formula. We just remember the steps. Okay, now you're probably wondering, when would you use the mean and when would you use the median? I mean, after all, they're both measures of central tendency. Why do they both exist? Why don't we just always stick with one or the other? Well, it turns out that there's some cases when we're better off with the median and some cases when we're better off with the mean. But what are those cases? All right, let me show you. It comes down to this notion of something called an outlier. Now, what exactly is an outlier? Well, within any data set, sample, or population, we may occasionally find a value that is dramatically higher or lower than the other values in our data set. Okay, so here's a quick example of this. Suppose you have 5 exams. You do really well in the first 4. The last one, let's say you're sick and you don't do so well on that final exam. The 48 is significantly smaller than your other scores. So you can tell, most likely something was wrong that day. And so this is why you only got a 48. So we can think of this as an outlier because it's substantially smaller than the other elements in the sample. All right, so by the way, we'll see later on, sometimes whether or not a value is an outlier is a matter of opinion, but there is a rule we can use to determine whether a value is large enough or small enough to be considered an outlier. So, we have to be a little careful with this idea. It's hard to say sometimes, what does it mean to be much larger or much smaller than the other elements? So there's a formal definition which we'll define, later on. But here, I think it should be clear that this 48 is so much lower than your other scores that we can think of this as an outlier. Now, this next one is interesting. Just a little explanation. You may or may not be aware that at SUNY Purchase, they have this program where retirees, meaning people 65 and up, can come to the school and take classes and pay a very, very small tuition. In other words, it's a tiny fraction of the normal cost. It's a program that the state of New York is running. And who is it really for? It's for people who, let's say they've retired and let's say they want to have something else to do. And maybe there are courses that they always wanted to take when they were in college and they never had time for them. Like, imagine somebody retires from a long career as a lawyer and then he decides to come back to Purchase and take classes in the English department because maybe he just wants to get back involved and wants to learn more about literature, for example. So the school has this program, and I've actually had a few people in my classes who are there for that reason. But what that means, though, is that within a class at Purchase, where you typically get people who are normally between 18 and 21, all of a sudden you've got somebody in the room who's 75 because they're one of those retirees who are taking advantage of this program. And you can see this list here. Clearly, the age of that person is well above the rest of the class. And therefore, that age could be considered an outlier because this person is significantly older than the other students in the class. And so we call that an outlier. Okay, so in other words, the outlier can be either much smaller than the other values, it can be much larger. Or here's another quick example. Imagine if I'm looking at the heights of the students in a class at SUNY Purchase, and the class contains a member of the basketball team who's 7'4". Well, his height is going to be an outlier compared to everyone else because he towers over the rest of us. The height of that basketball player could be thought of as an outlier because he's just so much taller than everyone else. So what does this have to do with anything? Why does this affect the decision as to whether or not to use the mean or the median to represent the middle of our data? All right, here's a good example. Imagine this sample. Now you might notice at the bottom there's a 100, which is way above the rest of the numbers. Clearly, that element is an outlier. So what we're going to do is this. We're going to calculate the sample mean and the sample median. And you'll see when we're done why in a case like this, we probably should use the median as our measure of the center. First, let's do the mean, which we know. Add up all 6 elements and divide by 6. Now that adds up, hold on. Get the old calculator here for a second. That adds up to 114. Now, 19 is the mean of the sample. Now, while that's technically correct, I would say that that does not do a good job representing the center of this data. Because if you look at them, look at these elements, let's say we sort them out, 1, 2, 3, 3, 5, 100. The mean is 19, which is significantly larger than 5 of the 6 elements. It is also significantly smaller than the 6th element. So in this case, the mean is distorted by the existence of this outlier. The mean is not giving us a good, accurate representation of the mean of all of these numbers. Let me just give you an example of how this could happen in the real world. Suppose that the average housing price in a neighborhood, well, let's just say that we have the homes in a section of purchase. Let's say there's some small section of purchase have the following values in thousands. Okay, so you've got one house that's worth 500,000, another house that's worth 600, 650, 700, and then 800, let's say. And then all of a sudden, we've got a house that belongs to Bill Gates. Somehow he heard about purchase and he decided to buy a house. And his house is worth $10 million. So that would be 10, wait a minute, hold on. 10 million divided by 1,000, that's 100,000 thousands. I mean, that's a gigantic number. Well, the last house belongs to Bill Gates. The mean is, and so we add them up. $17,208. $1,720,000. So in other words, the average value of the houses in this area is $1.7 million. But I think you'll agree that that would be a very deceiving number. It appears that everyone in this neighborhood is a millionaire when in fact they're not, because there's that one incredibly expensive house in the neighborhood. So in a case like that, you probably would not want to use the mean as the measure of central tendency, because it would give us a very distorted result. What would you do instead? Well, going back to our previous case, this one, why don't we calculate the median and see what happens? So we got 2, 3, 1, 3, 5, 100. And when we sort them out from low to high, you see that the mean, now the halfway mark would be here. There's 6 observations. You would average out the 2 in the middle, which by coincidence are both 3s, and you'll end up with a median of 3. So you've got 1, 2, 3, 3, 5, 100. The median is 3. So I think you'll agree that in this case, since the mean is 19 and the median is 3, our conclusion is that the median gives a more realistic look at the center of the data. All right, 19 versus 3. I think you'll agree that 3 makes a lot more sense than 19. The mean was distorted by the existence of this outlier. So as a rule of thumb, whenever we have outliers in our data, we tend to use the median as the preferred measure of central tendency. All right, because of the way they distort our results. So the conclusion is right here. Median is a better measure of central tendency when a data set contains one or more outliers. It can have more than one, by the way. But the existence of outliers throws off the mean as a measure, and in those cases, the median is the preferred choice. On the other hand, the mean is normally used when there are no outliers, because first of all, it's easier to calculate, and secondly, it has more convenient mathematical properties, which we really won't get into here. And also, I think it's just the case that for most people, the mean or average is intuitively more clear than the median. So in general, we use the median with outliers. The rest of the time, we use the mean. Okay, so just be aware of that. The median is a better choice when we have outliers. The mean is a better choice under other cases, meaning there's no outliers. So that's why we have both of them. If that wasn't true, then people probably wouldn't bother with the median at all. We would just always use the mean. So it's those pesky outliers that really make it necessary to use medians. Okay. Now, how about the mode? The third and final measure of central tendency, the mode. The mode is actually, in many applications, the mode is the least useful of the three. All it is the most frequently observed member of the sample or population. Which one shows up the most? That's all it is. So in a case like this, what you're doing is, like with the median, you're not actually using a formula. Okay, so let me just mention this here. As with the median, we must sort the data, and there is no formula. In addition, the sample and population mode are the same. So I just want to mention that it has that in common with the median. We have to sort. There's no formula, and therefore the result will be the same for median, sample, and a population. All right, so let's take a look at an example. Here's the mode. Here's the sample. So we're going to sort them out from low to high. And you can probably already tell what's going to happen. The only value that we see twice is 3. And that's what it means to be the mode. Okay, so in other words, once we sort them out, we'll see very clearly that 3 is the only repeated value. And that means that the mode of this sample is 3. And there it is. That's it. Now, here's where it can get a little strange, though. Unlike the median and the mean, there can be more than one mode, and there also potentially could be no mode at all. This is something we haven't seen up to this point. The mean and the median are unique. There's one for each sample or population. Here, it's actually possible for there to be no mode at all. There could be one mode, there could be 2, there could be 3, there could be any number of modes. So let me show you a case like that. Here's a sorted sample, and if you notice, it should be clear that 2 and 6 are both repeated twice, which means that both of these are the mode. All right, so 2 modes, 2 and 6. And not only that, but this is a special case. We have the special name reserved for these cases. It's called bimodal because, of course, as you know, the prefix bi means 2. Therefore, bimodal. And so that means if we had 3 modes, it would be trimodal. After that, I'm not sure. We'd have to look those up. But tri and bi are pretty clear. Now, having said that, what if there are no repeated values? Well, then, in that case, then we don't have a mode at all. Okay, so let me show you a quick example of that. What do you know? Nothing is repeated. Then there's no mode. And that's very bizarre. But it happens. There's no mode. It doesn't exist. All right, now you might say to yourself, well, how is this helping us? The mode is not, like I said, not the most useful of the measures. In fact, for numerical data, the mode is less useful than the mean or the median. On the other hand, this is where it comes in handy. The mean and the median are undefined for non-numerical data, such as colors, flavors, geographical regions, etc. In these cases, the mode is the only available measure of central tendency. So in other words, this is where it really comes in handy, not with numerical data, which is what we've been working with, but for non-numerical data, where we might be trying to figure out, for example, people's favorite color. For example, suppose that Apple wants to determine which colors to use for the next generation of iPhones. Now, I'm not sure myself what colors they currently offer. The one I have is dark gray, I think. Of course, you can pick any case you want, but the actual phone itself is dark gray. You know what, now that I'm thinking about this, let's find out. According to this, oh boy, here they are. The iPhone 13, here we go. There's 5 colors. You can pick pink, blue, midnight, or black, starlight, which is aluminum, white, or silver, and red. Now, here's the question. How did they decide on those 5 colors? Why don't you see green in there, or orange, or any of the others? Well, they would have done marketing research. So I'm going to add this in here. I think this is kind of a fun application. Let's try that. All right, here they are again. Pink, blue, midnight, starlight, oh my God, and red. These would have been chosen after extensive marketing research. Okay, so in other words, they would have literally contacted potential customers and said, listen, what color do you want? Now, they would have called and said, and what would have probably happened is that, for presumably, customers would have been asked about which color they wanted to see. The data would have been sorted by color, and then the colors chosen would have been the modes of the sample data. So in other words, it may be that there were 5 modes, and this is what they came up with. Okay, pink, blue, or it didn't have to be the case that they're all tied for the maximum, but they would have gone through and said, listen, what colors are people naming the most often? And the fact that they don't have green just means that less people name green than these colors. So in effect, they're using the mode to figure out what colors to produce, because that's what they expect to sell. If they ignore their customers' wishes, then people might switch to some other competitor's product. They can't afford that, can they? Absolutely not. Actually, this is interesting. If you look back in the early 20th century, you're probably aware that Henry Ford was the one who came up with the idea of mass producing cars so that they could be affordable by middle-class people. And then, of course, his sales went through the roof. But in the early days, all the cars, in order to make this possible, all the cars had to be pretty much identical to each other. And so, in fact, he was famous for saying at the time that you can have any color you want as long as it's black. He obviously at some point decided this is what people will buy. Therefore, all the cars have to be black. We are not capable of doing anything different. So at the time, the mode would have been black. After that, of course, they figure out how to make, keep the cars inexpensive and still offer different colors. But at the time, in the early 20th century, the only way that Ford could keep the cost of the cars down would have been to make sure that they're all exactly the same. Those were the days. Of course, he made himself a little money along the way. All right. Well, anyway, so now we have, before we do anything else, I want to introduce you to a special graphical device here. In statistics, there's several graphs that we can use to illustrate data. Here we're going to introduce one. There are several graphs that can be used to illustrate a set of data. And it doesn't matter if it's a sample or a population. One of the more popular ones is known as a histogram. So with a histogram, or a histogram is a series of bars. I'll draw one for you in a second. Each represents a range of values or a single value, and the height of each bar represents frequency of these values. All right, so just to give you a quick example, let's go back and revisit the case of the iPhones. You can imagine Apple summarizing their results in this way, although they might have used a different graph. So let's say that green wasn't a very popular choice. Let's say that 8% of the people chose green, and then next to it is yellow. Actually, I'm going to have to abbreviate these. Hold on, I'm running out of space already. Green. Maybe I'll just write smaller. Hold on. And let's say yellow wasn't all that popular either. Only 12% wanted yellow. And then all of a sudden, boom, We had a huge number of people who wanted red. Uh, 24%, and then black was 30%. And then we had silver about 24%, and pink. Actually, pink was very popular. Let's say this was orange. Anyway, the idea here is that each bar is a different color, and the heights represent the frequencies, or in this case, the proportions of people who said that's the color they want. So this is a very useful way of observing our data at a glance. In other words, often the data itself is difficult to visualize until you put it into a graph form, especially if there's a lot of data. So histograms are very popular in statistics for representing a set of data and how they are organized, and the frequencies of each value. So the graphs we're about to look at are histograms of stock returns. And what we're interested in, those certain characteristics of the histogram, because many types of data, many samples and populations may fall into one of these three categories. And these categories give us a lot of useful information about our data. And these look like very scary names, but when you see what they look like, you'll realize, no, this is something we want to know. Our data might be what we call negatively skewed, it might be symmetrical, and it might be positively skewed, although it doesn't have to be any of these three. It's possible that our data doesn't fall into any of these three categories, but if it does, it's useful to know that. The question is, how can you tell which is which? That depends on the relationship between the sample or population's mean, median, and mode, and it'll be clear from the histogram when these are the case. Let's start with the first one. Imagine we have a data set and we've calculated the mean, median, and mode, and we discover that the mean is the smallest of the three, followed by the median, followed by the mode. That's the category where we have negatively skewed data, which is hard to visualize until I show you the graph, and then you'll say, oh, I see what you're talking about. All right, so when this happens, the data is considered to be negatively skewed. Now remember, these are stock returns. So why don't we take a look at that graph and see what this is all about? Oh, okay, now here the bars represent returns. So in other words, for example, this tiny little bar down here represents a loss of 8.5%. Whereas way up here, this one represents a gain of 4.5%. So if you notice, 0 is right about here. So that means these are all losses. And these are all gains. And what we notice is that on balance, there's a lot more losses than gains. This is exactly what we do not want to see in our portfolio. And there's a particular pattern there if you notice it. The data stretches way out to the left. Okay, compared to the center region here, on the right, it falls off very, very rapidly. So in other words, the losses outweigh the gains. You don't want this for your portfolio. Also on the vertical axis, if you notice, instead of a percentage of the time, we're using the actual number of days in which this happened. Okay, so those are whole numbers. Beautiful. All right, now the second possibility is something called symmetrical. Now, the word symmetrical, you've probably seen it before, refers to a balance. All right, something is balanced. So here, what you're seeing is all three of these measures are identical to each other. And I think you'll like this graph. When the data are symmetrical, look what happens. Oh my God, that is nice. Look at that. These are gains, and these are losses. So the losses are matched or balanced by the gains. Or you can think of it as the left-hand side is a mirror image of the right-hand side. This is what symmetry means. It's the same on either side. There's a balance. All right, now what's the third possibility here? The third and final possible case is something called positively skewed. It's the opposite of this one, where you'll see when I get to it that the losses are smaller than the gains. In other words, this is the case we want to be true, but this only can happen if the mean is greater than the median, which is in turn greater than the mode. Just the reverse of what we had with the negatively skewed data. So what does this one look like? Well, this is the happy case. Very happy case. Because if you look at this carefully, you'll see that you're making money more often than you're losing money. Okay. Here we go. Gains are here and the losses are here. So the gains outweigh the losses. Wow, now that's nice. That's what we'd like to see with stock returns. Now, for other cases, that might not be what we want, but for stock returns, this would be the ideal. You're on balance, you're making more money than you're losing. But like I said, you may get cases where the data doesn't fall nicely into any of these categories. But if it does, it's useful information to have. Okay, so if this is your portfolio, it's good to know that you're on average doing better than good times outweigh the bad times. So, and by the way, if for data, just throw this in here. That does not fall into any of these categories. The bars would not have any particular pattern. So let me just show you like what I mean. What if we had something like this? Right, so as you can see, it doesn't look like any of our other three cases. It's just a bunch of bars. And so it does not fall into any of these categories. And you get this too. All right. All right. Now we're ready for the next set of measures. Now, these are more complicated than what we've been doing by necessity. So we're going to take these very slowly. So we started out with the measures of central tendency. Yes, but now we're moving into something new. Sometimes it's helpful to know not just the center of our data, but how spread out it is from the center. Let me just quickly show you what this is all about. We're going to introduce a group called measures of dispersion. So, like, for example, imagine I've got two histograms for two different situations. Let's say they both have the same mean. I'll just use the letter X here. P means probability of X. So let's say they both have a mean of 10 and they both have the same number of values. Okay, which if you notice in the left-hand case, most of the values are clustered right around 10. Let's say this is 9 and this is 11. Whereas here, the numbers are scattered all over the place. So even though they may have the same number of observations, I think you'll agree that these are two very different data sets. Here we have a high degree of spread. And here we have a very low degree of spread. Meaning that the data simply are not very widely scattered out. They're all really close to 10. On the right, a lot of these values are really not very close to 10. We need to know which is which. For many applications, this is extremely important. And in fact, talking about stocks, let me just quickly show you that in the case of stocks, the more spread out the returns are, the riskier is the stock. Okay, so in other words, in the case of stocks, the spread tells us how much the return can change from one year to the next. So the more spread out the returns are, the riskier is the stock. And that's important information when you're buying stocks for your portfolio. You want to avoid at all, normally you want to avoid risk unless there's a potential for higher returns involved. But at least this way you'd have a sense of how spread out the data are. So, the one on the left, the returns are very close to always being 10% from one year to the next, where on the right, they can bounce around from 6% some years to 13 or 14% in other years and everything in between. So as far as stocks are concerned, if the one on the left and the one on the right are stocks, the one on the left is a lot safer than the one on the right. Okay, now here's another case. Looking at these numbers, look at the values in the two samples. Sample one, the numbers are all pretty close to each other. In the second case, they're not. There's some of them are quite far away from the others. So the first sample is less spread out, and the second one is more spread out. And so the measures of dispersion are designed so that we can actually assign a number to each sample or population that tells us how spread out it is. Okay, so in other words, you can see just by looking at these that 2 is more spread out than 1. But it's not always easy to do that by just looking at the original data. That's why we need these numbers. So we can point to the numbers and say, yes, this one is really spread out, this one not so much. It's always good to have numbers for anything you want to do. That way you can compare them directly to each other. Right? That's the whole point. If we had 100 samples to compare to each other, we need to have a measure that helps us figure out which one is the most spread out and which one is the least. All right, now, now there were 3 measures of central tendency that we were looking at. We're going to look at 5 measures of dispersion. And again, some of these you may have heard of before, and some of them possibly not. So you can see that they are the range. We have something called quantiles. We have the variance, the standard deviation, and the coefficient of variation. Wow, that's a lot. But it turns out that some of these are actually related to other measures we've already seen. So it's not quite as much as it looks. But there are 5 that we need to know. And for the most part, the one that you're most likely to need is this one. At least in business. Okay, so like I said, I mean, if you're in a different discipline altogether, like biology, for example, or psychology, it's possible that one of the other ones might make more sense. But for business applications, almost without fail, this is the one that we typically use. Anyway, so because we're getting low on time, we'll just do the range today because it's very quick and easy. The quantiles are a bit messier. We can certainly save those for tomorrow. And by the way, as soon as we're done, I'm going to send out tomorrow's invitations. We don't want to go through that again. I always, unless I forget, I try very hard to get the invitations out a day in advance. It's kind of annoying to have to sit around and wait till the last minute. And, it was just because, it was just up to my eyeballs in exams that it happened. But as soon as we're done, I'll send them out. All right. So anyway, the range is exactly what you probably think it is. The range of a data set, whether it's a sample or a population, is simply the difference between the largest and the smallest element. And that's it. That's all you have to do. But if you notice, that implies that we're going to have to sort again. So like the median and the mode, there is no formula for the range. And the data must be sorted. Sample range and population range are identical. Okay, so that's the 3rd time we've seen this now, but don't worry, this is the last. After that, we need to distinguish between samples and populations, and we finally get to have formulas again. For the most part, okay. So let's go back to that sample that we've been looking at all this time. And we'll just do this. All right, those are the same 5 elements we've been looking at for a while now. And the sorted values are right here. Actually, no, let me do this real fast. I'll leave these up here as a quick reminder. All right, so we sort them out. -1, 1, 2, 3, 5. So literally, all you have to do is take the largest or the maximum and the smallest and subtract them. So the range is 6. That's it. That's all there is to it. Wow, that was simple. Whoops, ooh, I lost my place. Oh, here we go. I've got an example in the next slide that we can look at real fast. Another example, I mean. So yeah, the range is 6. That's it. That's all there is to it. Now, imagine we have a class of students and we write down all their GPAs. And I've sorted them out. The lowest is 2.2 and the highest is 3.5. Within that group, the range is the difference between these two, which is 1.3. That's it. That's all you have to do. Okay, so I think we can stop right here. We'll start with the quantiles tomorrow. We'll work our way through these other measures of dispersion. And then there's one more type of measure that we're going to need later on. And also, this is where we introduce that rule for determining how to decide if a number is an outlier or not. Okay, so that's coming up. So there's a lot of more good stuff in chapter 3. And if we finish it on time, maybe we'll take a peek at chapter 5. Okay, now remember, this is a very intense course. This chapter normally takes a week or so to cover. Here, it's probably going to be more like a day and a half. So yes, we will probably start 5 tomorrow, or at least look at it, and then we'll go through it very intensively on Wednesday. Then you'll have Christmas off, and then the following week we'll pick it up again at the same time. All right, so if there's no last minute, by the way, this version that I'm creating with all these handwritten notes, I'm going to post it on Moodle. The original version, which has no writing on it, is already there. I've been saving this with a new title on it. I've just added a date to it. So you can go back and say, wait a minute, I want to see those drawings of histograms that he did. Well, you can find them in this version of the slides. Okay, so in other words, we have the original version, and then we'll have this one with all my handwritten notes so that we don't lose them. Okay, you never know. I mean, it's like the whole point of writing on the slides is to give you more examples. So I don't like to lose them. And so you'll have them both if you want them. All right, so I hope you weren't too overwhelmed today, that you're not too frightened with this material. You shouldn't be, because as we get into it, you'll see that it just takes a little practice. We just have to get used to some new terms and some new concepts. And the calculations, for the most part, are really not that difficult. They're really more time consuming than difficult for the most part. So when we're done, remember, after 4 weeks, you'll have the equivalent of full credit, 4 credit or 3 credit or 4 credit course under your belt. So this is the best way, I think, to not waste your Christmas break. You know, have all the fun you want, but this is going to be very helpful to your majors, and also it'll help maybe give you a slightly simpler schedule in the spring. So this is the place to be, I think, during Christmas break. All right. So if there's no last,
I have a question.
Oh, yeah, go ahead. Please go.
Hi. Oh, well, it's actually not about this. Hi.
Hello, there you are.
I just wanted to ask you about another of your classes, the macroeconomic one.
Okay.
From the winter, which I'm in. I just wanted to like check and make sure that all of my work, like that you had it.
I remember seeing it. I'll tell you what. I'll let you know if I'm missing anything. I'm like I said, I'm up to my eyeballs in exams to correct and all. So if there's any issues, I'll let you know right away.
Okay, thank you.
Okay, you're welcome. All right, William, bye.
Sir. So I just wanted to double check, when is the first problem set due?
Oh, I would say probably next Monday.
Okay.
Yeah, you've got plenty of time. It's already sitting there right there. Already you can do a large percentage of it. If you look at it carefully, you're just going to be asked to do some of these same measures. So if you want to get started early, you certainly can feel free to do so. But you won't need to have them ready till next Monday.
Okay. And then in terms of like if we have a conflict with a class, because
Yes.
I actually had to have a pre-existing conflict for Wednesday.
Right.
Should we know you if that's the case?
You know what? You can if you want to. It's not absolutely necessary, because I'll assume that if you're not there, you're going to watch the video anyway.
Mhm.
But yes, it would be nice to inform me of that, because what sometimes happens, unfortunately, is you get people who sign up for the class and then they don't come to the classes and they don't watch the videos either. We don't want any of that.
Yeah.
So yeah, I mean, if you let me know, it would be very, very helpful. But you know, because, you know, online, it's a very different ballgame than in person. And I can tell who's taking it seriously and who's not. So, so yeah, if you can't be here, you can't be here. That's the beauty of the online system. You can just watch the recording, and and it's not the same, but it's still, it's all there then.
Yeah. And sorry, I just had one more quick question about the material, actually. So I know that you mentioned that the median is different for a sample versus the population, whereas or sorry, I mean the mean, whereas like the median and the mode are the same for a sample and a population.
Yes, they are.
Besides the notation for the mean,
It's the same too. It's just that the notation is different.
Okay.
That's how we tell them apart, but the actual calculations are identical. Yes, you're right about that. That won't be true for all of these measures, though. There are some where the two are actually mathematically different.
Okay.
So, but yes, you're absolutely right. For the mean, when you do the calculations for the mean, median, and mode, it'll be the same whether it's a sample or a population. But it's important to distinguish between the two cases.
Yes.
And so when there's a formula involved, we use the different, you know, the Greek letters, for example, with the populations, just so we can tell which is which.
Mhm. Okay. Yeah, that makes sense. Thank you so much.
Okay, you're welcome. All right, who's next? Haley.
Hi, sorry, me.
Oh,
I think I'm muted. Hi. Yeah, sorry. So I haven't had a chance to go through the book too much. But if we need like any extra, like we feel like we just need some extra practice,
yes.
should we just like kind of as we go along in the book, just do book problems, or do you
You can
have
do
like,
those,
or
but
should
then
we
you-
reach out to you?
If you do the book problems, though, you won't know if you got the right answers, though. So,
Oh, there's no answer key. Okay, got
well,
it.
actually, no, you know, there maybe there are like the odds or the evens. I don't remember. They might be there,
Okay.
but yes. But I find that the for whatever reason, the book writes the questions in a very odd way. I find that people have trouble understanding what they're asking. I don't know. I think it might be easier if I write my own extra questions for you, because I looked at them the last time I taught this class, and I was like, why are they making them so complicated? You know what I mean? It's like, it just seemed
Yeah.
like I wasn't sure in some cases what they even wanted to know. So you can do that, but I would recommend you just say, listen, can you give me more practice problems? And I'll take
Got
care
it.
of
Okay, great. Thank you. And I'm sorry, you said if we can't be in class, is it like
Yes.
every time you want an email, or just like
No. It's fine.
we'll just make sure to like
Yeah,
watch
I mean, just in
videos
general,
and
keep me up to date, what's going on. But yeah, you can watch the recordings. Like I said, if you go to my YouTube account, like even this one, it takes a while for the recording to be converted to the MP4 format, but I'll post it there when it's ready. And then you can watch it whenever you feel like it. It's just like any other YouTube video. And
okay.
so that way, and even if you just want to watch it for certain parts over and over again, you know, that's fine.
Got it.
So
Great.
the
Thank you so much.
quality is actually pretty good because I mean, it is YouTube, and so you know, you never know. Like there might be one little thing you missed, or there might be maybe you or somebody called you in the middle of it or something. So you can watch the whole thing, or you can watch a little of it, or none of it, but it'll be there. And if you can't find it, let me know. Or very occasionally, I forget to post it, and then you can just say, "Hey, please post it," or something like that, because it's not unthinkable that I could forget about it.
Okay. Sounds good. Thank
Okay.
you so much.
All right, you're welcome.
Take care.
All right, bye. See you tomorrow.
You too. Bye-bye.
Okay, bye. All right, anyone else? You're welcome, everyone. All right, so I'll see you tomorrow. And I'm going to send out the invitation in a few minutes so we don't forget about this. And then when the video is ready, I'll post it on my YouTube account. Okay. It takes a while for it to convert, but it should be ready very soon. All right, see you all tomorrow.